Hey everybody, thanks for joining us. I'm Professor Corey, this is Professor Victoria, and we are the Professors Du Bois, and today we're going to give a little lecture about how we can calculate concentrations of solutions using a unit of molarity. So this is a good one.
All right, solution and ion concentration. So reactions, we've been working with reactions and predicting the products of reaction, double displacement, single replacement, and precipitation, gas forming reactions, all of these types of reactions. And we're going to switch over from qualitative to quantitative within those reactions. But we're working with solutions. And when you're working with solutions, you might have questions like, well, how much chlorine am I going to put in my pool? I have a 5,000 gallon pool. How much of this am I going to need to put in? If I want to make hydrogen gas and I'm using magnesium plus hydrochloric acid, now you know now that if we add magnesium and hydrochloric acid together, we can predict those products. We can predict the hydrogen is going to be produced, but how much do we need, and how much of that solution, of that hydrochloric acid, can we use? So we've been working with masses, and now we have to switch over and say, well, how are we going to quantify the solutions? So we have measures. We can measure our solutions. We can measure volume with it. But if you have solutions, you might have hydrochloric acid in that same example. You might have something that's very dilute hydrochloric acid compared to very concentrated hydrochloric acid. So you would add different quantities of either of those for a reaction. So how are we going to manage this quantifying the solutions and knowing how dilute or how concentrated something is? That's where we're starting for this lecture.
So we can't use mass for a solution. Let's just think about an aqueous solution. We can't just weigh it because, imagine a solution of salt in water. If there was just a little bit of salt in there and we weighed 10 grams, it would be very different than if there was a lot of salt in there. So we need to know how much salt is in that solution. And the unit we're going to use is called molarity, and it's represented with a big M. And this is one of those derived units in disguise. If you remember when we started, geez, that was a long time ago.
Sure.
We talked about units and how derived units were made up of two or more base units. Well, molarity, the big M, is actually moles divided by liters. It's moles of solute, that's what's being dissolved, salt, per volume in liters. So I don't like to write the big M. I like to write mole per liter. And you can, anytime you see something with a big M, you can replace the big M with the mole per liter. And I think that's just helpful. And you'll see why when we start with these calculations.
So here's an example. Find the molarity of a 100 ml solution that contains 0.25 moles of dissolved solute. So this concentration that we're solving for, doesn't even matter what it is. It doesn't even say in the problem what the substance is. As long as you know how many moles you have, you can figure out the moles per liter. So we have to convert our milliliters to liters. And then we can simply divide our moles by our liters to get our molarity. It's that simple.
And if you're not familiar with that milliliters to liters conversion, that's one to write down or practice. We'll be doing that a lot. A lot of these questions give you volumes in milliliters, and we need to go to liters for molarity.
True.
So here's another example, and this, not a whole lot of work here because they gave us the moles, but they did give us the salt this time, sodium chloride, and we're in 0.75 liters. So we can calculate the molarity very simply by taking the number of moles, it's moles of solute, over liters of solution. It's the entire solution, 0.75 liters, and when we do that division, we get 0.28. I like to write mole per liter, mole over liter, the way it is here, but it's also okay to write big M, 0.28 molar NaCl. Another thing you'll see is oftentimes they'll put brackets around the salt or whatever it is that we're measuring the concentration of. And those brackets indicate that this is the molarity. This is the concentration of this salt.
Yeah.
And we've got the unit there, tells us it's molarity.
3 different ways to represent the same thing. And if you're going to use this as a factor, we're going to get into using molarity as a factor, right? We use our derived units. When we have more than one, you'll want to write it like this. But they all mean the same thing, molarity, concentration of a solution. We can also determine the ion concentration. So we talked about sodium chloride dissolving, and they break apart into 1 sodium and 1 chloride ion. And of course, the molarity of the sodium chloride would be the same as the molarity of, say, the sodium ion, because one of them breaks into 1. But what if we have something like calcium chloride? 1 calcium chloride would dissolve into 2 chloride ions. So our chloride ion concentration would really be twice as high. So we can use our canceling units to be able to solve for this. So if we're provided with, or if we have to calculate a molarity of the overall salt, oftentimes we have to calculate then the ion concentration as well. So here's our calculation. We have moles per liter. Oftentimes we've been used to just having 1 unit here to start with. It's okay, just put it over there. Our liters is in the denominator. We're going to use our stoichiometry from our balanced equation. So we have 1 calcium chloride breaks apart into 2 chloride ions. So our moles of calcium chloride are going to cancel here. We're left with moles of chloride ion per liter. That liter stays there. So we have moles per liter remaining. These moles cancel, and we're left with moles of chloride ion. And we could have also put it in brackets, 1.06, and that means molar.
I think they would put the chloride ion in the brackets, and then it would say 1.06 molar.
Okay. That's better.
Okay, so this one, just takes it a little step further. We've got 15 grams of a salt, and it's dissolved in 500 mils. There's that mils again. So we're going to need to convert that to liters, and we also need to get moles. And this is simple. We've done this before. We're just going to take the mass of this salt, and we can use the molar mass from the periodic table to determine the number of moles. But the first thing we want to do is write the balanced equation. So they're saying that this salt is dissolved, and they want to know what the sodium ion concentration is. So when we write the equation here, you can see that there's 2 sodium ions and 1 sulfate ion for 1 sodium sulfate. So I'm looking at the coefficients. So the way I approach this, I'm going to start with my 15 grams and then use the molar mass. It was provided, but we can get that from the periodic table, and I can get the moles of the Na2SO4. Now, to get molarity, I have to divide by the total volume in liters. So we did that. We didn't show how we divided. We didn't set that up, but we did that in our head. So that's 0.500 liters. So we end up with the molarity, or moles per liter, of the sodium sulfate, and then we can use this. It's really reaction stoichiometry to go from the moles of the sodium sulfate to moles of the sodium ion. Now, you could do this another way. You could have got the moles of the sodium sulfate and then went to moles of sodium ion and then divided by the liters. It really doesn't matter. But in the end, we just have to have units, moles divided by liters, and we get 0.028.
Here's your chance to practice. So here's an example. We have also going from a mass of our total salt. So you want to write your balanced equation for the dissolution. You want to break this apart into its ions. Make sure you balance it. And then you can calculate your molarity of your salt, your molarity of your salt, and then you can convert that into the molarity of your ions. Or you can calculate the moles of salt, convert that into moles of your ion, and then divide by the total volume in liters to get your molarity.
So one thing to point out here is that that nitrate ion, now that ends in 8, right? That's a polyatomic ion. So you might want to look at your polyatomic ion chart to realize what that is, that might help you out.
Right.
And
yeah.
it looks like there's 3 of them. Just saying.
Hint, hint. Pause the video and give it a try. All right, here's your answers. And we have shown you 2 different ways to do this. We've kind of described it in words. Sometimes listening to words is a little bit hard, but you have one approach up top here where we have converted to moles of our ion. So we converted to moles of our salt, and then we did our 3-to-1 ratio here from our balanced equation to get the moles of the ion. We still need to divide by the total liters of the in the flask. So this is 250 milliliter flask, means 0.25 liters, and then we end up with our molarity. And in this case, we just put it a capital M. Otherwise, you can also calculate your moles of your salt, then convert that into molarity, moles per liter, and then use your balanced equation to change it into the molarity of your ion.
Yeah, so be careful with the, just mole, the way you write mole. Keep that lowercase. Molarity is the big M, and so you don't want to be writing big M for mole, because molarity is moles divided by liters, and you can get yourself kind of confused there. So I think one thing we never mentioned too, and this is really funny, is you probably noticed mole, we write it as MOL. That's actually the abbreviated form of the full word mole, which is MOLE. And I just
saved a lot of time.
I just find
E.
I find that hysterical.
We couldn't use M because that's meters. Lowercase m was meters, so
yeah,
we were kind of stuck there.
Mole.
Okay.
All right. Thanks for watching, everybody.
Thanks for watching. Stay tuned for our next installment of the Professor's Du Bois channel.
Bye.
Bye-bye.